Well, good morning, everybody. I hope you're ready for another wonderful, fun-filled day in 307. Today, we're going to be looking some more at gas-liquid systems and trying to investigate how we can delineate the compositions of multi-component systems where both a gas and a liquid phase are present. Now, yesterday we looked at gas-liquid systems, but we're really only focused on, the application of Rault's law when there was only one condensable component. And so today we're going to look at what to do when there are multiple components that can condense within the system. I think this is going to be a really helpful lecture and really vital lecture, particularly as it applies to the case study. So I'm going to try to go a little slower today and make sure I can emphasize these major points. And as well as answer any questions and clarify things as much as possible. So, oops, don't want to lose that. Recalling from yesterday when we looked at gas liquid systems, we had focused specifically on the application of Rault's law, which, if we remember, Rault's law for a single condensable species states that the partial pressure, which is equal to the mole fraction times the total pressure, also relates to the vapor pressure of that substance at the temperature specified, where the vapor pressure is determined by one of several things. We used Antoine's equation a lot. And we can also use Clapeyron equation. Clausius-Clapeyron equation. And Cox charts, various ways to do it. Like I said, this is, I'm going to put a little star by Antoine's just because it's, the data is available in the back, and it's kind of the most direct way to do it. And so with that in mind, we can get ideas in terms of how to break down information associated with the compositions of gas liquid systems. Keeping in mind this is at equilibrium. And so if we're not at equilibrium, we can't make the assumption associated with having that partial pressure being the vapor pressure. Is there any questions on that? We also talked about the dew point, right? T sub delta P, which, the dew point is where the vapor pressure is equivalent to the saturation pressure. Right, and so for that, looking at Rault's law for this system, This pi star now is T delta P, or on the dew point. And if the vapor pressure isn't the saturated pressure, then we have a superheated vapor, and we can't use dew point data to find the vapor pressure. So we looked at a couple examples yesterday on doing some calculations involving Rault's law, both at and not at the dew point. And so what we're going to look at today is moving a little beyond that and considering what to do, like I said, when there's multiple components in the system. And what we're going to look at are several examples and several applications of both Rault's law and Henry's law as it applies to these systems.
I have a question.
Yes.
For bubble point, would it be the same, like your P star is equal to your P saturation? Would it be the same for bubble point as dew point?
Not, it's similar, but it's different. We'll get to that at some point today, I believe. But it's not exactly the same.
Oh, okay. Alrighty, thank you.
Because we're looking at things a little differently. And we'll talk about that when we get to it. It's, yeah. But that's good that you're making that connection, but it's a little different in how we interpret the equations in regards to dew point as opposed to bubble point, because dew point, once we have a saturated system. However, for bubble point, a lot of times the system isn't going to be saturated in the vapor phase, which is what allows us to have that bubble formation. But like I said, we'll get to that here in a second. So looking at vapor-liquid equilibrium for multi-component systems. And so for these systems, we're largely going to rely on approximations, which are forms of Rault's law, and Henry's law. And so what these equations are going to let us look at are relationships between various things. We're looking at having functions associated with the partial pressure of a substance, the mole fraction of that substance in the vapor phase, and the mole fraction of the substance in the liquid phase. So these relationships allows us to specify our material balances such that we can get an idea of the breakdown for components in the liquid and in the vapor phase. So when we're looking at Rault's law in these systems, we can state the partial pressure of the substance, which we've already identified as the mole fraction in the vapor phase times the total pressure, but we can approximate it as the mole fraction in the liquid phase times the vapor pressure of that substance as a function of the temperature in the system. And when we look at Henry's law, we have a similar equation where the partial pressure of the substance, which is equal to the mole fraction, and the vapor phase times the total pressure, but it's equal to the mole fraction in the liquid phase times some constant that isn't the vapor pressure as a function of temperature. And so this H sub I of T is known as the Henry's law constant. And Henry's law applies, here I'm going to use a different color. When the composition in the liquid phase is close to 1. So when you're looking at systems or components that are high in a certain species, we rely more on Henry's law. And we use Rault's law when we're looking at more dilute substances. Oh, I think I got that mixed up. Excuse me. I'll say that makes way more sense. I think I just did it again. All right. Let me redo that. So for these approximations, Henry's laws apply when we have dilute solutions of X sub I. And Rault's law applies when we have rich solutions of X sub I. I get those confused sometimes. So let me really do a quick recap. And so these two expressions allow us to connect the mole fractions in the liquid and the vapor phase of a component as a function of two variables: the vapor pressure, or the Henry's law constant, and the total pressure. And so knowing 3 of these 4 values allows the final value to be calculated. And so when we're looking at vapor liquid systems in equilibrium, particularly for multiple component systems, we can rely on one of these 2 expressions depending on if we're dealing with rich solutions or with dilute solutions of the component of interest. And the only thing that's a little tricky is for the Henry's law constants. These are empirical values that must be looked up. If I wanted to give you this on like the final, I would give you the Henry's law values that you would need for a particular problem. So let's look at an example. So if I had ethane in air, and it was really dilute, 1 mole percent of ethane in air, which is in contact with water at 20 degrees Celsius, and the pressure is 20 atmospheres. How could I determine the mole fraction of dissolved ethane in the water? So which expression am I going to use? Am I going to use Henry's law or Raoult's law? If we had 1 mole percent in the air,
Henry's law?
we would most likely look at Henry's law, because if the mole fraction is low in the vapor phase, we're probably going to see an even lower value in the liquid phase. So it's probably going to be something that we can assume is dilute. And since it's going to be dilute in ethane, we would use Henry's law. And so Henry's law would tell us that this relationship applies. And so this would be 0.01, P would be 20 atmospheres, XI would be an unknown, and we would have to look up H sub T for ethane and water at 20 degrees Celsius. And so that Henry's law constant at 20 degrees is about 2.63 times 10 to the fourth atmospheres per mole fraction. And so that tells us that the composition of ethane in the water should be Y sub I times P over H sub T, or 0.01 times 20 atmospheres over 2.63 times 10 to the fourth atmospheres per mole fraction, which is equal to approximately 7.6 times 10 to the minus 6 moles ethane per total moles. So extremely dilute in ethane, which makes sense. It was low in the vapor phase, and water's not particularly soluble for a gas like ethane. So let's look at one more example. Let's calculate the composition of a vapor in equilibrium with liquid that is 10 mole percent benzene, 10 mole percent toluene, and I believe the remainder, 80 mole percent, is nitrogen. Actually, I'll make it easier. I'll say the liquid is 50 mole percent benzene, 50 mole percent toluene, and we don't need to worry about the nitrogen. We're just going to have a 50-50 mix of benzene and toluene, and we want to know the composition in the vapor space above this benzene and toluene. So are we going to need Raoult's law or Henry's law? I'll give you a second to think about it. I will be right back. All right, can you guys hear me okay?
Yes.
Wonderful. So did you guys take a vote while I was gone? What do you think, Rault's law or Henry's law?
Henry.
All right, we got Henry's law. For this one's a little trickier, right? Because it's not really technically rich in either phase. But at the same time, it's not lean, right? It's literally 50-50. I would say though, since both of these substances are similar in structure, the liquid's gonna behave uniform. And we can assume, based on that Rault's law is more likely gonna apply. And we would find, even if we used Henry's law, the constants that would be obtained for Henry's law in the system is going to be such that Rault's law is going to be really close as well. So you're going to probably get the same result. So it's, at the end of the day, it's maybe not going to matter as much for a system like this because the substances are a little similar. But I would use Rault's law primarily because the vapor pressure data is a lot easier to find than Henry's law constants. And so with that in mind, I know a trick question, this was kind of mean. We can use Rault's law to get an idea of the vapor composition. And so Rault's law tells us that the mole fraction times the total pressure is similar to the mole fraction in the liquid times the vapor pressure at that temperature, where T is 30 degrees C. And so what we need are some ways to calculate vapor pressure for these two substances. So my instinct is to go straight towards the Antoine constants for both toluene and benzene. So if I run over to the constants in the back of the book for benzene, I have A equals 6.89272. B is equal to 1203.531. And C is equal to 219.888. For toluene, I have A is equal to 6.95, 805. B is equal to 1346.773. And C is equal to 219.693. And once again, for this, reminding you that it gives your vapor pressure in terms of millimeters of mercury. And the expression looks like this, B over T plus C, where T is in degrees Celsius. So looking at benzene, I have the log of P star sub B for benzene is equal to 6.89272 minus 1203.531 over 29 or T, excuse me, which I believe was 30 degrees Celsius. So 30 degrees Celsius plus 219.888. So what does the vapor pressure of benzene come out to be? Millimeters of mercury.
$119.
119 millimeters of mercury. All right, now let's look at toluene. Which is log pressure of toluene equals 6.95805 minus 1346.773 over 30 plus 219.69. So what is the pressure of toluene?
$37.
So we have only 37 millimeters of mercury, right? So now we have the vapor pressures of both. So we're looking for the composition of vapor in equilibrium with this 50-50 liquid mixture of benzene and toluene. And so since they're in equilibrium, these vapor pressures should add up to the total pressure in the system. And so the total pressure is simply 119 millimeters of mercury plus 37 millimeters of mercury. And this is only because it's in equilibrium. And so what we should get from this is the total pressure being somewhere on the order of, let's see, no, I shouldn't say that. I have to back up. I jumped the gun a little too much. It would be the total pressure if they were 100% of these components, but they're only 50. So the total pressure should be the mole fraction of toluene times the vapor pressure of toluene plus, here I'll write total, the mole fraction of benzene times the vapor pressure of benzene. And it might be a little confusing as to why. And if we look at the expression YIP equals X sub I P star, right? Or I should say for toluene and for benzene, if we add these two expressions together, we'll get something that looks like this. Y sub T times P plus Y sub B times P equals X sub T times PT star plus X sub B times PV star. And then if I factor out P, what is this value? Y sub T plus Y sub B.
That's 1.
It's unity, right? They're the only two components. If that's unity, I'm left with total pressure is equal to X sub T times PT star plus X sub B times PB star. And so application of Rault's law also lets us figure out, based on the values we have, what's the total pressure. I figured it was worth the while to doing that really simple derivation so you can kind of see where I'm getting these equations from. And so with that, the total pressure of the system should be the partial mole fraction, the mole fraction of toluene, which is 0.5 times its vapor pressure, which we said, I think, 37 millimeters of mercury, plus the mole fraction of benzene, 0.5, times the vapor pressure of benzene, which was, what, 119? Yes. And so what does that give us? That gives us about
78.
78 millimeters of mercury. I think I lost part of my screen. So now that I have my total pressure, I can solve for my mole fractions, right?
I have a question.
Yes.
If you're finding P, like if you were trying to find the fraction in the gas and you were trying to find the vaporization pressure, would you do that in the reverse sense? You know what I mean?
Repeat that.
So
Trying to make sure I'm understanding your question.
just how you factored out the 1 in the gas phase
Yes.
and you were looking for total pressure. If you were looking for the vaporization pressure of the mixture, could you factor out your total in the liquid?
That's harder to do because the pressures in this case would have to be equivalent so that you could do that factorization. Does that make sense? And that's
Yes.
almost never the case.
Okay.
But that's a fair question. And so now to solve for our mole fractions, we can use Rault's law one last time and state the mole fraction in the liquid of benzene times the vapor pressure of benzene over the total pressure gives us our mole fraction, or 0.5 times 119 millimeters of mercury over the total pressure, which is 78 millimeters of mercury, which should equal about 0.76. And that lets us know toluene is about 0.24. So with a 50-50 mixture of liquid benzene and toluene at equilibrium with its vapor, the vapor will be 76 mole percent benzene and 24 mole percent toluene. So it would look something like this. So if I had a container and I put a 50-50 benzene toluene such that, excuse me, we had that liquid kind of settle in this tank, we let it come to equilibrium, and then we extract the vapor in the headspace, right, where this is still your 50-50 mix. The headspace would have 76 mole percent benzene and 24 mole percent. I know this is ugly, I'm sorry. Toluene. Now, let's say I took that vapor and I condensed it into a liquid. And so I had now 76 mole percent benzene and 24 mole percent toluene. And I wanted to do the same thing again. I let this system come to equilibrium, and then I wanted to know, well, what's the mole fraction of benzene and toluene in this headspace? How could I solve for that? And I'll say this is at, for the sake of simplicity, 30 degrees as well. Such that the vapor pressures are the same, right? Well, my total pressure I could calculate as I did before with the mole fractions. But this time I have 0.76 mole percent of benzene and 0.24 mole percent toluene. So what would my total pressure in this system be? I get about 99.3 millimeters of mercury. And so with that, the mole fraction of benzene in the vapor space here would be 0.76 times 119 over 99.3 millimeters of mercury. Or I get 0.913 benzene, which tells me my toluene mole fraction is about 0.087. Or since I had it in mole percent on that, I would say 91.3 mole percent benzene and 8.7 mole percent toluene. And so I had a 50-50 mix. I allowed the liquid and vapor to come into equilibrium, and I got 76 mole percent benzene, 24 mole percent toluene. I condensed it and I allowed it to come to equilibrium again. And then I had 91 mole percent benzene and 8.7 mole percent toluene. And so you can start to see a pattern. As I take these mixtures and I condense, allow it to come to equilibrium, and recondense, I notice that the vapor space begins to become enriched in benzene or have a higher benzene content. And what you would find also, if you kind of did a balance in terms of looking more closely at, what would be the mole fraction leaving if we actually looked at quantities leaving, these bottoms would become more and more enriched in toluene. And so this is the exact principle that distillation columns operate under. And what we have in this system are mixing systems. We use trays typically in a column. Sometimes you can use packing. But the way it works is we essentially design it such that, in each little subsection, we have some liquid and some vapor coming to a pseudo equilibrium so that the vapor becomes enriched in one component, in this case benzene, and the liquid becomes enriched in a second component, in this case toluene. And so you have all these equilibrium stages at the top and the bottom of the column, such that you have benzene primarily coming out the top and toluene coming out of the bottom. And it's through this applications of these vapor pressures as a function of composition that this enrichment occurs. I think that was a good way for me to illustrate, the importance of this vapor-liquid equilibrium and how it relates to an actual unit operation in chemical engineering and in engineering in general, right? Taking advantage of this equilibrium relationship allows us to separate mixtures to high purities. And so what that means is if I want to get really high purities of benzene, I just need more of these equilibrium stages, is what we call them. Which means I need to make my column bigger. If I don't need it as pure, I can make my column smaller. Now there's a couple other things that we can look at. Oh, I think my thing had a little trouble. My computer might be getting a little overheated. See if I can turn the screen sharing on. But that is the main principle of how distillation columns work. And so another way at which we can kind of visualize this vapor-liquid equilibrium is through what's known as TXY or PXY diagrams. This is typically for two-component systems. And so the way these diagrams look is I'll show you kind of a TXY diagram. And so what you're going to do for, let's say, a TXY diagram is for fixed pressure, say 1 atmosphere, you would have one component on this x-axis. So for example, I would put mole fraction benzene and for the next component, I would have, let's say, mole fraction toluene. And so this would go from 0 all the way to 1. So no benzene to pure benzene, no toluene to pure toluene. 1. All right, so ticks along the way. And the way this diagram would look no, actually, no, that's silly. I did this wrong. There's temperature. That makes way more sense. It would look like an envelope where below the envelope, you would have liquid. Above the envelope would be vapor. And in between is where the equilibrium would occur. And what you would note, okay, is where the mole fraction at benzene is 0 would be a temperature. And this would be the boiling point of toluene, of pure toluene, right? Because that's where the vapor and liquid of toluene would come together and meet for a system that's pure toluene. For a system at pure benzene, which is over here where mole fraction is 1, that temperature would be the boiling point of benzene. And everywhere in between, we would have the toluene and the benzene being partially vaporized as a function of the composition. All right, and so this would be the VLE envelope for this mixture. And so it would tell you, let's say I had that 50-50 mix of benzene, and I would put that in equilibrium with its vapor at a specific temperature, right? So this T would have been 30 degrees. That would have told us what the composition of benzene would be in the vapor phase that's in equilibrium with that liquid that we fed it at that specified temperature. And we could have looked at that for any sort of mole fraction. It would have given you, let's say for 0.1 or something mole fraction of benzene, it would have said, okay, that mixture is going to boil at this temperature, and the equilibrium or the composition of the vapor phase would be this point. And so what we call these are kind of like tie lines. And we'll talk about those more when we look at ternary diagrams, but they denote, you know, the connection at these specific values of the liquid and vapor that are in equilibrium. Are there any questions? All right. Let's talk a little bit about some more terms. I know Mitch had mentioned looking at bubble point, which is, it's a little different than dew point, but the bubble point temperature and there's a bubble point pressure. And so the bubble point temperature is the temperature at which the first vapor bubble forms in a liquid when slowly heated at a constant pressure. And this is different than the bubble point pressure, which is the pressure at which the first vapor bubble forms when a liquid is slowly decompressed at a constant temperature. And so that's why it gets a little tricky to denote, you know, a true bubble point, because there's different ways in which it can be measured, looking at it in terms of its temperature or its pressure. And the bubble point temperature is largely going to depend on the pressure in which it's measured. And the bubble point pressure is largely going to be determined by the temperature at which it's measured. And this goes, you know, it's very similar to the dew point. You know, we looked at that water table or the steam table to find information about the dew point of water at various pressures. And you can do a similar thing for bubble point, but you have to be sure that you know what type of bubble point you would like to look at. All right, are there any other questions? I think that's a good stopping point for today. What we can look at is maybe one or two more examples, looking at a gas liquid systems tomorrow, and then we'll get started at looking at solid liquid equilibrium. All right, if not, thank you guys for attending. I will, sorry, I don't think I had a chance to finish looking and at the midterm adjustments and releasing that to everybody, so I will do that today. And if you still don't have that information, feel free to politely bother me via email to make sure I do that. But if not, take care, guys. I hope you have a great day.